hertz per picofarad per amplifier as a figure of merit. The moment I go for a two-stage amplifier, my figure of merit has been reduced by the factor of 3, right? But what advantage I will get here is that I'll get the larger swing at the output, right? This is, I think, similar thing it is mentioning. It is okay, similar thing. Yeah, here it is saying that GBW max is nothing but FT3 by 8. Already we have seen it previously, right? It is a maximum GBW or gain bandwidth you can achieve by the single stage is FT by 8. And with the telescopic, again, it is FT by 8, right? So that it is best to use the telescopic amplifier, right? Because you are getting the very huge gain, no noise contribution, right? No noise contribution by additional transistors, or no extra noise contribution compared to the single stage, and GBW is also same, and because of that figure of merit is also same, like 1000 megahertz picofarad per milliampere. So that if you are not bothered about the swing or output swing, you can always go with the telescopic amplifier. This is personally prefer, as well as many designers prefer the telescopic amplifier over the other amplifier because it gives the larger figure of merit or better figure of merit uh, with the higher low frequency gain, right? No noise, that is also very much important point to note. And apart from that, it is having the input reflect noise is also very less compared to the single stage, as you are having the higher low frequency gain, right? So that this telescopic amplifier is very good as compared to single stage amplifier, right? Uh, but again, only problem with this kind of architecture is swing, right? Now there's another amplifier people are using quite frequently, that is a symmetric amplifier. At first instance, you will find that you will see that it is nothing but uh, nothing but a two-stage amplifier, but unfortunately it is not a two-stage amplifier, it is a single-stage amplifier, right? Because at this you will find that gain is 1, and this gain is 1 is getting multiplied over here by the second stage, right? This CS amplifier means here, even though it is a CS amplifier, it is having gain approximately 1, and from here, where this stage, that is M8 and M6, will give the gain which is required, right? And what is the disadvantage of this architecture? You will get gain bandwidth is GM1 divided by CL into B times. It is just a straightforward method, just straightforward thing is because you are pumping larger current, you are getting the larger bandwidth, nothing else, right? But what is the beauty of this architecture? What is the beauty of this architecture is, it is, if we see fully differential pair sees everything is similar, right? Means whatever M1 transistor sees around, similar kind of things M2 transistor also sees around. So that uh, this kind of architecture is very much good when offset is or mismatch is one of the concern while designing a circuit. So that even though you can spend a little bit more area, but you will get uh, good performance in terms of a mismatch, right? Because if something is symmetric, then always circuit is happy to uh, take into the account, right? Then whatever we have done to increase the gain, similar kind of thing we can use along with the symmetric as well, because we it's till now, according to our understanding, if we put the cascode thing, it gives only better performance at the cost of swing, of course. But always it is better to have a telescopic at the output or a cascode at the output, right? Because if swing permits, right? Because you will get a lot of advantages over others, and What is the figure of merit? Is figure of merit is 1000 divided by 6. 3 is coming, 3 into 2 is coming because of B I have selected as a 3, right? B I have selected as a 3, and it is a 2 branches. It is flowing through, current is flowing through both the branches at the output. So that it is 1000 divided by 6 time your figure of merit. Apart from that, apart from the whatever figure of merit has been reduced in this kind of architecture, uh, apart from that, designing having some critical issues over here, because your GBW will further reduced, right? Further reduced because your first non-dominant pole will be seen over here, right? Means it is nothing but your CGS of M4 plus B times CGS of M6 as coming over here. So that if your B is quite large, then first non-dominant pole will come quite closer to the lower frequency, so that you have to push your GBW also at the very low frequency. So that this is hidden into this FOM. This is not explicitly mentioned. But if we mention that also, then GB FOM will reduce further, right? So that with this, we can say that our telescopic amplifier will be having good FOM, and simple single stage differential amplifier having the good FOM, right? Then FOM of folded cascode, right? Folded cascode is having a lot of buzz over the design among the designers. It is kind of a people may say that it is very high frequency circuits, and I can design this those circuits with the folded cascode. But those are really true or not, that we have to verify first, right? Then considering what it is, then bandwidth is nothing but 3 dB bandwidth is nothing but 1 upon 2 pi Rn4 into Cl. Rn4 is output impedance looking at the output node, right? And what is the GBW? Gain bandwidth is nothing but GM1 by Cl. It is similar to all the other architectures, right? But what is the figure of merit? Figure of merit is divided straight away by 2 compared to the single transistor, because there are extra current which is flowing through these branches, right? So that uh, in folded cascode, if somebody says that I can have a very high speed and all, it may not be true as such, because the moment if I wanted to uh, increase the bandwidth, right? I have to pump extra current into this, so that I have to drive the transistor area will increase, right? Transistor area will increase, and because of that, CGS will increase further, so that non-dominant pole will come at a lower frequency. Uh, then somebody will argue that, okay, I'll play with the area then, instead of to increase the GM, right? Instead of pumping current, I'll increase the voltage overdrive to increase the GM, right? But unfortunately, in this kind of folded cascode, generally people won't prefer those kind of thing, because already you are compromising with the output swing, right? And if you increase or play with the area to increase the GM, then again it is harmful, because you will further reduce your output swing. So that generally it is not preferred to to play with the area to increase the GM. Instead of that, pumping the extra current into output branch will help to improve the GM, as well as because it will not damage your output swing, as well as it will improve your speeds, right? So that it is some designer will prefer those kind of approach, right? So, but biggest advantage with the folded cascade is still, I did not mention over here why people are using folded cascade in their designing. Uh, Folded cascade is very good and extensively used in a sensor-based application, particularly automotive sensor-based application, because of its uh, very high input common mode range, right? If any architecture, if we take previously, it will not reach to the below zero level, input DC level, right? Then in this architecture, you can easily achieve that. Assume this source of M3 is zero point 0.2 volt. Suppose VD sat is 0.2 volt for every transistor. Then here it is a zero point 0.2 volt. Here it will be, you can say 0.4 volt, right? So that VDS of VD sat of M2, then this VGS can go zero point 0.4. If VGS is zero point 0.5, then it can go to minus zero point 0.1, right? So that principally speaking, even practically speaking, you can go below zero level, right? So that is definitely very much advantageous for a sensor-based application where your sensor output comes at the somewhere wiggling over the ground, and you have to amplify that, right? So that in folded cascade amplifier, that is a key advantage, so that people are using this architecture quite frequently. It is not definitely for a better figure of merit, because if you wanted to have a better figure of merit, you can go with a telescopic, right? uh, but yeah, this architecture gives the better performance for a very high input common mode range, particularly zero to rail. And folded cascode, now trend is like that. Folded cascode people are here. I have shown with the PMOS as a input differential pair. People can use the NMOS along with this PMOS input differential pair, so that rail to rail goes input common mode range of this kind of architecture are huge. Yes, you can drive any kind of common mode common, and you can satisfy any kind of common mode requirement. And this is principally why it is I'm emphasizing in this on this point, is that it is it is giving relaxation to your neighbor, right? Because you are designing your operational amplifier and somebody else is designing the previous circuit and this, then always you are helping to the other guy to decide his or her common mode range, anything between the rates, right? And that is also one of the biggest advantage, because you are helping other designer by relaxing their specification, right? So that folded cascode is very much popular in that way. Now we'll do the comparison. Uh, telescopic telescopic cascode. Telescopic cascode is only swing is a problem. Otherwise, figure of merit is one of the best. Uh, Not actually, it is not a speed. It's a figure of merit. Figure of merit. FOM divided by. You have to read this column like FOM divided by 1. FOM divided by 6, FOM divided by 2, FOM divided by 3, right? So that according to that, telescopic cascode gives one of the best performance in terms of FOM, and where symmetrical SB is equal to 3. Symmetrical having other issues as well, but yeah, speed is the FOM is not good. A folded cascode FOM is divided by 2, and Miller again it depends on the B, right? But here, whatever B we have selected as a 2, right? And for that, FOM is 3, right? If B is more and more, your figure of merit for a Miller 2 stage will fall further, right? I total, in fact, I have considered into FOM itself, so that even though if you don't get into the I total, it is fine, because FOM will contribute it, or already having those into the account, right? In terms of a noise, symmetrical is performing very badly, because all the transistors which are connected into the circuit is contributing to the noise, right? And telescopic folded cascode Miller stage is almost only driving transistors and transistor which is connected to the rails only, contributing to the noise, nothing else, right? Because cascode is having that beautiful advantage. Okay, before going ahead, I would like to take any questions if anybody is having.
Yeah, anybody has any questions? Dr.
Hello,
Vinayak, I
sir.
had a small yes, yes, please go on, Madhuri.
Huh. Sir, I have a question. That sir, on the 12th slide, you mentioned about three regions: weak inversion, strong inversion, and velocity saturation. Sir, so what
Mhm.
are the applications of these regions? Means, for which application we should go for which region?
Okay, okay, one
Can
second. I'll come to that. Yeah, here, right?
yes,
Yeah.
sir.
In weak inversion, generally it is like you are operating your transistor with the below at the below threshold, right? That means, principally speaking, you are not allowing any current or very less amount of current flowing through the transistor, right? You are allowing very small amount of current flowing through a transistor, right? And particularly, it is it this kind of circuits means weak inversion circuits are used where power is very much critical, but when you are designing implantable devices where power is very much important uh, or very much concerned, then at that point, generally people used to design their circuits with the weak inversion region. But disadvantage with this kind of thing or this kind of circuits are that they are very much sensitive to the VGS, right? Because your drain current is exponentially dependent on a VDS, right? And apart from that, this circuit is also very much sensitive to the thermal variation, because you can see that ID is equal to exponential VGS divided by VT, so that uh, so that if you are really sure that your temperature is not varying significantly and your VGS is not varying significantly, apart from that your requirement is very very less power, then generally people go with the weak inversion. Now coming back to the strong inversion is generally people use, that is in general whatever designers are using nowadays, it's strong inversion. And last is a velocity saturation people don't want it to go in, but technology is pushing designers to go in, right? Means nobody design your circuit, generally nobody design their circuit into the velocity saturation region, because it
So,
is a finally it is a linear, right? Means you don't want your VGS is increasing with the same proportion of ID. At least you should have a square relation, right? If I'm giving 2, I should not get the output 2. At least I'll expect 4, right? So that generally people don't prefer this to get into the velocity saturation. Apart from that, it is limiting your GM as well, so that
okay.
either people will stick to the SI boundary of SI and VS when you require the very high frequency, right? And if you are concerned with the power, then people go in the boundary of black and red. Hope I'm clear.
Hello, sir. Huh.
Yeah,
Sir, high frequency boundary of SI and VS, right?
yeah, yeah, yeah.
Okay.
Right.
And for a weak inversion, when we have to go for lower means low power.
Yeah, yeah, exactly. Look.
So implantable means is it for biomedical application or
Uh, yeah, generally biomedical and implantable when I'm talking about.
okay? Okay, sir. Thank you.
Yeah. Any other questions? Because we'll move to next topic now, our next operational amplifier kind of arena.
Dr. Vinayak, can you go to slide 48? You had shown one symmetric op amp, right?
Yeah, one second. Yeah, here.
So this is symmetric because of the push-pull.
It
I
is
mean,
symmetric
you are
because differential amplifier sees the symmetry. That's way I understood this.
okay. No, because the path from M1 to the output goes through two stages, whereas M2 to output is only one step. So I was just thinking in those lines.
Okay, you are saying is that no, I did not
M1
get
to
what you're saying.
if I have an input at M1, the negative input, it goes through two mirrors first before it reaches the output node, whereas from M2 it's just one step.
Okay, right.
So
I
the delay
understood.
from
Yeah, I understood your point. If we use this fully differential, then it is a fully
huh,
symmetric amplifier, we can say.
yes, yes,
Your point
okay.
is right. then we
So
can.
this is symmetric because it has pull up and pull down equal strength, I suppose. I
Yeah,
mean,
I think that way also we can think of. Yeah, that is one of the point. But I have seen only differential amplifier
okay,
is a symmetric, so that I call it as symmetric. But
okay.
yeah, that is also one way. It is a push-pull kind of architecture, we can say.
Hmm.
Yeah, thank you.
Uh, yeah.
Uh,
Any other questions from the participants?
Hello, sir.
yeah, yeah,
Yes.
please.
Hello. Sir, in folded cat score, that is slide number 50, you talked about the advantages ICMR, input common mode range, that can go in negatives. So can you elaborate this point?
Oh, okay, yeah, yeah, sure. Suppose I have assumed my VD set is 0.2 volt, right? So that
Okay.
at the drain of M10, yeah, sorry, drain of M10, you will find a 0.2 volt, right?
Okay.
And similarly, here also you can go up till point 0.4, right? Then for getting point 0.4 at the 3, at the node 3, how much VGS is required? Then point 0.4, point 0.4 and VGS of this minus VGS of M1, right? Suppose VGS of M1 is point 0.1, point 0.5, right? That is quite a legitimate number. Then 3 node is having point 0.4 volt, and I can go gate of M1 till minus point 0.1, right? Point 0.4 minus point 0.5 is minus point 0.1, so that I can cover the ground also in an input common mode range.
Okay.
That way I understood and pretended.
Okay. Point 0.4 minus point 0.5.
Point
Minus
0.4
point.
minus point 0.5. Yeah, VGS is VGS of M1 I have assumed as a point 0.5,
Okay. Okay.
right?
So point 0.4 minus point 0.5. So that is minus point 0.1.
Yeah, yeah. For example, I am taking this number, but yeah,
Okay.
generally
Okay.
this number goes into this range only.
Okay.
Okay.
Okay. Understood. Thank you.
Yeah. Then we'll move little bit complicated circuit hereafter, because this will be kind of a last part of our presentation. This is the sub 1 volt configuration. As I said, that as technology is permitting only till where I have worked is only till 1 volt for nominal transistor, where this architecture was published in 1997. Uh, this architecture was quite popular because it uses digital as well as analog concepts. Uh, we forget about the digital at time being, where you can say that 2n is a clock, where ms and m11 is getting on and off. We are assuming those are on only, so that there is a short between these two short between drain and source of ms or ms, yeah, ms and m11, right? If you look at closely, then what it is, this is a differential amplifier, right? Simple differential amplifier. Now you are folding back the current, right? And here, this output you are pushing into the second stage, right? And this is nothing but a CS amplifier. That means what it is, this is a folded cascode, and this is nothing but a second stage, the CS amplifier. This is two-stage amplifier, right? But it operates as a 1 volt, as it is already shown. Uh, but what is the beauty of this architecture is, uh, you can have a rail to rail input with the two stage. And when I was reading this paper, this CC is creating the LHP0. Yes, I don't know how to explain it, but you can go back and read this. The CC is creating the LHP0 so that it can increase its gain bandwidth quite significantly. So that and this was the advantage of this architecture, right? And yeah, this is the first stage, and here it is a second stage. This is a lot more complicated. It's very difficult to. Previously, I have mentioned the input there. It was quite visible. Here, it is not at all visible. But if you look at carefully where the inputs are here. If you see my marker, you will find that very easily, right? And if I wanted to analyze this circuit, then again we can analyze like this is we can leave this. We can assume that there is a current source. This is a differential pair. We are folding back the current, right? Here also we are folding back the current, and after that again this is next amplifier, right? Means roughly we can analyze or visualize the circuit what it is. It is nothing but again similar. First stage is folded cascade and second stage is I guess what it is. Second stage, yeah, second stage here again. Second stage is again CS amplifier, right? But what is the disadvantage and advantage of this circuit? First of all, it works at the uh, 1 volt, and surprisingly, when threshold voltage is 0.7 volt, right? So that this is quite interesting to analyze. Apart from that, it is a bulk driven transistors, right? So that why it is a bulk driven, because uh, by giving bulk and making the bus source junction as a forward bias, you can always reduce your threshold voltage uh, and and operate at the lower threshold voltage, so that you can reduce your VDD further, right? So that I'll not get into the details. I'm just giving this circuit so that you can go back and read it by yourself, because at least at the first instance we can analyze this folded cascade, and this is the second stage, right? This is a third circuit. It is again uh, similar to what you can say, input input is driven by the gate driven input transistors. This is the first stage, and again it is a folded cascade, right? Here we are folding the current, and this is conventional folded cascade. Only addition what this author has done is he has connected the CX over here, right? And as CX is connected over here, top plate is positive and bottom plate is negative, so that uh, input differential transistor will be bulk driven, not a bulk driven. It have bulk is having bulk and source will be in a forward bias direction, and forward bias direction will reduce your VTH, and after that you can analyze very easily, right? But again, this kind of here they have written that VT is reduced from 0.6 to zero point 0.4 by bulk bias, right? So that the CX will help to establish it will act as a battery to bulk and source potential of a differential transistor, right? But again, this kind of architecture um, you may design or you may review in your coming days, where you have to concern, as I have discussed, is noise, right, and the mismatch, because as GMB terms comes into the picture, it is very uh, it will reduce your noise significantly. But in this kind of architecture, one more danger why practically people are not preferring this kind of circuit is that this value of CX. If VBS potential, if you do it little bit higher voltage, your forward bias junction may get significantly active, and your current will start from bulk to source, right? And that you don't want, because while modeling the transistor, you have not considered that current, so that it is it is in generally people avoid this kind of architectures, because it is quite risky, because with the temperature also your junction will leak, and if with the process variations, if CX will hold a larger amount of charges, your junction will forward bias and start leaking quite significantly, right? Because it is having some exponential relationship with the current. So that this kind of architectures works at a very low VDD, but but has some potential risk along with. These architectures are uh, again very popular. I have mentioned this architecture over here because uh, this have designed with one of our colleague who is Shauri Chatterjee, Professor Shauri Chatterjee in IT Delhi, right? So that I have mentioned this architecture. This architecture is very popular as well as works at very low VDD, right? The VDD he has worked on is, I think it is a zero point 0.5 VDD, where threshold voltage of that 180 nanometer 180 nanometer CMOS itself was zero point 0.5 or 500 millivolt, right? So that he made the circuit to work at a zero point 0.5 volt, right? But again, what he has done that we'll see carefully, he has used two transistors, like this M1A and M1B are the input transistors, right? And bulk he has driven by the another extra voltage, right? So that this uh, threshold voltage of a input driven transistor can be reduced further, right? By forward biasing the bus source junction. And apart from that, if you look at carefully, M4A and M4B is nothing but a back-to-back transistor. It creates a positive feedback, so that gain is primarily is given by these two transistors, so that he can operate at the very low voltages as well as with the enough amount of gain, right? Apart from that, uh, he has used these two high value resistors. I think it is for common mode feedback generation. And from CC and RC, you can guess that it is nothing but he has used for a compensation of second stage, right? Fine. But that way, I think whatever I have understood, I have explained to you, but you can go back and study it little more on this architecture, because this architecture is very popular because it works at a very low voltage, right? And I think this is one of the architecture which he has primarily done during his PhD. I think he has done from Columbia. Okay, this architecture is one of my favorite architecture. Uh, if we look at this carefully, there, then this is nothing but a super buffer, which we call it as super buffer. This M2, M3, and this current source, this configuration generally call it as a super buffer. Why it is called as a super buffer? Because this V2 will appear over here, means at the source of M2, right? With almost all the value means almost accuracy of or multiplication factor of 1, right? That buffer has to do, right? So, and if you look at carefully, then M1 transistor is having gate at M1, gate at V in 1 and source at V in 2. Means principally speaking, this whole architecture is nothing but a single transistor differential amplifier, right? That is the beauty of this architecture. And because of that, you can say VDD is equal to zero point 0.9 volt. It operates at very low voltage, right? But again, it is a single, what you can say, single output or single, not fully differential circuit, right? And apart from that, this architecture is quite nice, but only thing is that your input is differential, that is V in 1 minus V in 2, but output is nothing but uh, output current is uh, is proportional to square of difference between two the difference between input transistor. That generally it is disadvantage, I can say, for so to say, for this, because output current is not linearly varying with the input. It is having some square root relationship with input, and generally it creates a non-linearity, so that even though you can operate or you can design your circuit with the minimum amount of transistor, but you should somehow deal with this non-linearity of output current. right? And this is an inverter for analog. Inverter is quite popular architecture because inverter is equally famous in digital domain as well as analog domain, right? Because in a digital domain, yeah, definitely everybody like to invert their bits, and in analog domain, if we see this region which is quite linear, so that somehow if are able to keep the Vout or stabilize the DC operating points of the output node, then this inverter, we can use it as an amplifier, and uh, no amplifier performance matches with this, right? Why it is so, I'll just explain you. Uh, First of all, swing is it's like out of the world, right? You are having only two transistor into the rail, so that you are having very good swing. Apart from that, if you see the graph, it is a very linear, right? This is second advantage. Third advantage. Third advantage is that it is kind of a push-pull kind of architecture. You can see both the transistors contributing to the output, right? Equally contributing to the output. So that it is kind of this kind of a third advantage means you are giving input to one input only once, but both the transistors acting on the input to give the output, right? So that this is one of the best scenario that anybody can want. And apart from that, it improves your figure of merit quite significantly, right? Why it is so? Uh, uh, because in fully differential amplifier, which we have seen previously, single-ended, it is having figure of merit 1000 megahertz picofarad per milliampere. And here I am using only single branch, so that I can improve the figure of merit by the factor of 2, that is 2000 megahertz picofarad per milliampere. And apart from that, here I am using the class AB kind of structure. Both the transistors are working, so that again multiply by 2. So that figure of merit is for this simple architecture is nothing but 4000 megahertz picofarad per milliampere, so that it's like a cracker to the design fraternity, right? So that it it for very high figure of merit, if anybody wants, then inverter is the only way where you can go with, right? But yeah, previous architecture is a single-ended, so people came with the differential because concept is very convincing, so that people came with the this kind of architecture, right? Where this is the input, this is one end, and this is the second end, right? And 5x transistor of PMOS and NMOS, that is direct connected transistor, is connected to just uh, help the CMFB to work, right? Because if we study carefully, there are two current sources. One is like a bottom current source and a top current source. And if output goes up, that is principally can happen, which that is why CMFB comes into the picture, right? If both the output node goes up, gate of bottom transistor goes up, so that uh, source of VREF comes down, this node comes down, at the end this node comes down, so that at the output comes down, right? So that this node sorry goes up, this is comes down, right? Fine. Okay, so that this is how the CMV works for this. And even though if we analyze the figure of merit for this, 1000 divided by around 5, the current how much flowing through this, sorry, 4000 divided by 5, still it is 800 megahertz per megahertz picofarad per milliampere is the figure of merit for this. It's still very much higher than the uh, many architectures which we have studied, except simple single stage amplifier, right? But here your swing linearity is quite high. Then we'll go quickly to the multi-stage amplifier, right? Multi-stage amplifier is nothing but, which we have studied already. This is single stage amplifier, right? This is GBW is nothing but GM1 divided by CL. Already we know that it is a two stage. Then first non-dominant pole is because of M2, that is GM2 divided by CL. But here you carefully look at GBW is nothing but GM1 by CC, right? And now I have connected another thing or another stage, that is a third stage, that is nothing but GM3 divided by 2 pi CL, right? If we look at carefully, then in previous, and this is nothing but, in previous GBW is GM1 by CC when it is a two stage, and non-dominant pole is GM2 by CL. Here again GBW is GM1 by CC and non-dominant pole is GM3 by CL, right? Means non-dominant pole is almost it is getting created because of the uh, final stage. Again, it depends on the value of GM2 and CD and others, but still, for a better design or optimized design, we can think like this. Again, whatever we have studied from previous side, we can say that uh, here we have said that non-dominant pole is 3 times greater than GBW. Previously, we have said that 2 times, uh, right? And second non-dominant pole, which is getting created because of the third stage, it should be 5 times GBW, right? Why this, from where this 3 and 5 number is coming, that is quite interesting. It is coming because the moment you started selecting these value, you will get the Butterworth response. It is called the Butterworth coefficients for a gain bandwidth and related pole values, right? Fine. Then but before going ahead, it is multi-stage amplifier figure of merit is by the thumb rule. For previously we have said that 1000 megahertz picofarad per milliampere, but here for a three-stage amplifier is divided by almost by decade, so that if by the multi-stage amplifier, if even though if we are able to achieve the figure of merit of a what you can say 100 megahertz picofarad per milliampere, then also it is considered to be a very good amplifier, right? Then before closing this slide, I wanted to mention that your second pole should be 5 times GBW, right? So that it is kind of very difficult to achieve this without pumping larger amount of current, right? So that for achieving this 5 times GBW, definitely you have to pump a lot of current so that you can push this pole to the, or this non-dominant, second non-dominant pole to away from the UGB further and further, so that your phase margin is very well maintained. Right, we'll just plug some numbers so that you'll get the idea, right? GBW is 50 megahertz, CL is 2 picofarad, and ID1, IDS1, IDS2, IDS3, CC, and CD. Then we have to find this. Then with this calculation, you can figure it out. IDS1 31 microampere, IDS2 95 microampere, and IDS, it's around, this is 10 times of this, right? 315 microampere. But also frequency is also similarly 150, 50, 150, and 250, right? So that from this we can see that we have to burn a lot of current, or we have to burn a lot of power to achieve this multi-stage behavior. And apart, and even though if I'm not connecting the compensation of RZ and or any zero compensation, it works fine, because either you have to come or compensate by feed forward or RZ, or you can pump very huge value of current into the successive stages. So both the way you can do, either you can do some smart way, or you have to pump the current by the regular way to improve the phase margin. right? Now, few configuration we will study now. This is nothing but a two-stage, and this is nothing but a three-stage. Signs are very carefully we have to select. And first, the first stage, it is no matter what sign you have opted for in between input and output. But second stage, surely it should be non-inverting, and third stage should be inverting, right? Then only we can say that there is a negative feedback, because this CC2 will create a negative feedback, right? And CC1 will create a negative feedback over here. So that it is primarily you have to follow the sign convention to have negative feedback in action. This is also one of the interesting circuit. This is called the differential pair, and this is current mirror. But if you see carefully, uh, this is not a differential pair as such. And can you guess which is the faster and which one is the slower? You can give a thought for a minute, right? Look at carefully what it is.
First one is fast, I think.
First one is fast and second one is slow. Means first means, I mean to say, it is a left hand, right? Left hand is fast and right hand is
Yeah,
slow.
exactly.
Okay. Um, can you gauge any, what you can say? Can you give any reason for that?
Yeah, it could be because in the second side there is a mirror pole over there actually.
Okay, mirror pole over there. Okay, fine. Uh, any other answers? Okay. I think you can see it carefully. This differential pair it's I think it's not a differential pair as such. It is, again, it is a folded cascode kind of thing. Right? We are folding back the current which is going through this to this. One second, I don't know how to make it big. I have to come all the way. Differential pair. Okay, what it is nothing. But here we can say that the current which is coming through over here, right? Here also you can see the two transistor. I mean, that means it is that is again, it is like a 2 CGS it sees. And here also, if current goes over here also it sees the 2 CGS, right? So that these two, according to my understanding, these two circuits are having the similar kind of frequency behavior as it is, right? Because this current also sees 2 CGS, this current also sees 2 CGS, right? So that there is a uh, nothing much, but at least in second you will get the larger swing as compared to the first. That is the only difference I found. But yeah, both the circuit principally can operate at the exactly same frequency. Hopefully, I think you agreed with this. If no, then just you can ping me later or mail me later. We can discuss. This is a multi-stage amplifier, and this is a very, very popular multi-stage amplifier, which we call it as a nested Miller compensated amplifier. And whatever we have seen previously, it is same. This is nothing but this one, nested Miller. This is also nested Miller. As I said, that GM1 block can have any sign, that is minus or plus, right? Just for analysis, we have to do it little bit carefully, because output will be then non-inverted if I say that GM1 is minus, right? And if GM1 is plus, then output will be inverted. That you have to, that is the only difference. If so that there is no constraint while selecting the GM1 block or designing a GM1 block. Then GM1, GM2, GM3. CM1 gives the negative feedback. CM2 gives the negative feedback. CM1 also overall gives the negative feedback. So that architecture-wise, it is really correct, right? But previous architecture having the problem is that you have to select the values of CM1 and CM2 is quite large, or GM2 and GM3 values quite large, so that you can push your non-dominant pole very, very far from UGB for Butterworth response, 3 and 5 times of a UGB, right? But here, with this kind of architecture, you are having some feed-forward paths, right? Already we have known that why feed-forward paths are there. It is actually for compensating the zeros, because when there is a capacitor connected between input and output, you will have the current passing through that at the higher frequency. It creates a zero, right? It is nothing but output is shorted with the input, right? So that how this GMF2 is working is that how much current is getting pumped by the CM1, GMF2 is started sucking exactly similar amount of current at the CM1. That is basic principle behind this. And again, if you look at closely, what is GM2 by CM2? If we select GMF1 and GMF1 is equal to GM1 and GMF2 is equal to GM2, then we can have a compensation, right? And non-dominant poles are nothing but GM2, CM2 and GM3 by CL. I don't know whether I have written it. Okay, fine. But yeah, this is actually, we are replacing the resistors which we can connect into the connecting into the series with the CM1 and CM2. This is just replaced with the other differential pair of a transistor. Means similar kind of device you are using for a compensation, right? And again, disadvantage is that you are losing the power in while designing the GMF1 and GMF2. If we connect the resistor as a passive device, so that there is no constraint on the power, so that figure of merit will be reduced little, but again, it will not reduce quite significantly, because you can compromise by selecting, you are pushing the UGB a little harder at the higher frequency side. Now here it is something like GMF2, right? The GMF2 is equal to GM3, right? And here these are two non-dominant pole, GM1 and omega 1 and omega 2. Now principally what we have to do, this zero should cancel one of the pole. This is the first dominant pole, first non-dominant pole. This is the second non-dominant pole, right? And this is the zero. If I select this kind of architecture, right, where GMF2 is equal to GM3, right? I think it is not mentioned over here. GMF2, okay, that is not mentioned, but yeah, from here, this equation, you can see that this zero will cancel this first non-dominant pole, right? It will not exactly cancel, but at least it is closer to this, right? Means first pole will come, then zero will come, right? It is nothing but a pole zero duplet, and it will cancel each other's effect. 1/2 is still, it is not very good, but it's okay. Means you are doing some mistake and immediately you are correcting that. Similar kind of thing is happening over here, right? Means your first non-dominant pole will come, right? And it will start degrading your response. Then immediately next zero will come and nullify that. Means after double the frequency, right? And this is again 2 into GM3 divided by CL. Again, this is second non-dominant pole that you can push it to the further and further by at least pushing the GM3 with the higher values, right? So that generally second non-dominant pole comes at the very high frequency. As we have compensated the first non-dominant pole with the zero, you can having the liberty to increase the unity gain bandwidth, right? Similarly, whatever we have seen in previously, similar thing architecture wise, only it is different. Here it is like you have to compensate this non-dominant pole now, right? First non-dominant pole, that is GM2 by CM2, right? Now we have established the fact that we have to somehow compensate the non-dominant pole, because first non-dominant pole, because it is problematic. It is reducing my UGB, right? Then what these architectures are doing is that they are creating one zero to compensate that first non-dominant pole, so that they can increase their unity gain bandwidth, right? This is the fact. uh, this is the thing people are using to design this, all these architectures which we are discussing, right? Then this is the first non-dominant pole, we have to compensate with the zero. Then you can see closely GM2 divided by CM2, and here it is a GM2 divided by CM1, but there is a multiplication factor of GM1 and GMF0. Means we can select the value of GMF0 such a way that this value will be closer to this value, and always it is tracking with each other, because these equations you can see is closed with each other, so that they are always tracking with each other, and we can select the value of GMF0 such a way that it will cancel the first non-dominant pole, and you are having the luxury to increase your unity gain bandwidth, so that you can increase your or improve your figure of merit. uh, and all these architectures were presented around 90 to 97, right? But after 10 years or so, this is first architecture came, which talks about the fully differential multi-stage amplifier, and it precisely used the similar kind of architecture, right? And here we can quickly see that what it is. This is nothing but a folded cascode. Now you are very much familiar, right? This is, I think, this is folded cascode. This is the first stage. This is the second stage, and this is the third stage. This is CM. They have connected. CM. They have connected. We have to connect CM2 as well, but I don't know. Anyways, you can go back and see this, right? But it is again three-stage fully differential amplifier, first published at ASSCIRC. It is at Europe's one of the best conference. This is again the comparison multi-stage amplifier. This is single stage amplifier. Phase margin you can get up till 90 degree. And SMC you can get up till two stage, that is simple Miller compensation, you can get till 63 degree. But again, you have to compromise with the GM values and all those, right? This is nested Miller compensation, that is 60 degree. This NGCC, NFC, NMCF, MNMC, these are the some topologies, multipath compensation, something like that. All these are the three stage, and phase margin you can get around 60 degrees and all, right? So that now I think we have established a stage that you can easily take any paper and start reading by analyzing the circuit visually itself. These are some interesting other circuit which was published in 2002 kind of year. But here, very interesting thing about this architecture, it is having one positive feedback inside, right? If the CM2 is connected with the positive feedback uh, in terms of positive feedback to second stage, right? And this is CM1, it's again negative feedback. But generally it is observed that even the positive feedback into loop, if negative feedback is stronger than the positive feedback, then positive feedback will not affect much, not at all affect. So that this is the circuit, and this is the equations for that circuit. And this is very, very important to understand that this is a open loop gain. This is a dominant pole which gives the minus 3 dB, and these are the zeros, and these are the poles, right? Even though if we don't bother about anything, you can easily see that there is a difference between omega 2 and omega 3, right? If somehow we are able to, I have written no, yeah, Yeah, somehow if we are able to make W3 and W2 by selecting the proper value of GM3, GM2 and associate values of capacitors, then we can completely get rid of any non-dominant thing, right? Then it is as there is no non-dominant exists, you can push your omega d quite significantly at the higher frequency, right? This is the Ramos architecture, which he has presented in CSEC 02. This is the same architecture. Architecture is very simple. You will sometimes I also wonder that how can't we publish this kind of thing. Okay, this is a folded cascode. This is a CM2, and this is a CM1. This is a folded cascode. This is a the second stage. This is the third stage. 2 RCS amplifier, right? And here CM2, instead of connecting to V0, it has connected back to this node so that it is creating the positive feedback, and this is CM1 which creates the negative feedback, right? So that architecture is very simple and gives very good performance, but involves a lot of math around this to understand how non-dominant poles are getting cancelled by the zeros. And because of that, you can see that gain bandwidth is 6 times larger than the uh, nested Miller compensated multi-stage amplifier, or three-stage amplifier, right? It is quite possible because there is no non-dominant pole exist thereafter. This is another architecture published in JSSC. Uh, Here, if you look at closely, the compensation is given by the this branch, and this symbol is having some significance. It is nothing but it shows that Ahuja's compensation. Ahuja compensation was published, if I remember correctly, it is in 1983, and those kind of compensation is heavily used by nowadays also. It is also called as an indirect compensation, means you don't connect a resistor or something, you can connect through some cascode kind of architecture and emulate R is equal to 1 by GM of something. And those kind of architectures are quite popular nowadays, right? And here you can say again that this gives 41 times better performance than nested Miller compensation, right? I don't wanted to get into uh, such a complicated discussions of expressions, but here again, if we look at closely, this is a zero, and these are the zeros and these are the poles, right? And you are having some factor kt in your hand, right? Kt, that is gm2 divided by gmt, like it is kind of some variable in your hand so that you can exactly match both poles and zeros with each other so that you can get rid of all non-dominant factors which are limiting your uh, UGB, right? Uh, Again, that architecture, whatever architecture, complicated architecture we can see over here, it is, if we get into the circuit form, it is it's very easy to understand. This is nothing but a folded cascode, right? This is I guess, this is a second stage. This is just mirroring. And this is the third stage. And this is two factor to program this GMT, because we have to program the GMT to get the exact value or required value of KT so that you can cancel this poles and zeros, non-dominant poles and zeros, right? Uh, I'll keep last 15 minutes to discussion, right? This is a case study which we have designed in 2018. This is minus 3 dB bandwidth enhancement technique, right? And this is nothing but a simple differential amplifier, first stage, and this is the second stage. If I don't connect any C over here, then I'll get P1 and P2. That is well-known fact. Phase margin is very poor, that is 10 degree, right? Then I have connected the then what we have to do is that we have to connect. One second. This how to get the stable response is they create a dominant pole in system to make a single pole system which is inherently stable, right? That till now we have established the fact that single pole system or dominant pole system uh, is inherently stable because it gives the phase margin close to 90 degree, right? So that what we have to do is that push the P1 to the uh, we have to connect the CM so that P1 is getting pushed to the lower frequency and P2 is getting pushed to the higher frequency after UJV. That is, this is dominant pole and this is first non-dominant pole, which we are talking about. But this Miller compensation gives hit in terms of a reduction in a 3 dB. And reduction of 3 dB generally it is not good for designing many systems. Generally, people want larger 3 dB so that they can operate at a very high frequency with a similar kind of gain, right? So how to tackle this? Then we started studying this circuit. Here is a V1 and here it is a minus K into V1 when capacitance is connected. But if I wanted to keep same, but the moment this at the high frequency capacitor starts conducting, right, this V out will start falling, right, at the higher frequencies. That is nothing but a zero is getting introduced into the circuit, right? If I don't want it to get zero, then what? Just cut the branch. Or other words, in terms of a circuit, if I wanted to say, then connect the value of resistors whose value is infinity. Connecting the resistors value is infinity, similar to that. So that you will not get the zero, but at the same time, you will not get the Miller compensation effect as well, right? So that somehow I have to connect the CM to the V out to get the Miller, but at the same time, I I wanted to resist the current also. So what we have done is that this is again the Ahuja kind of compensation. We have connected, this is a Miller compensated, Miller capacitor, and we this one by GM3 will act as a resistor, and we can change this GM3 by by varying the W by L of this branch, or W by L of this ratio of this transistors, right? Ratio of these two transistors, M11, M12, and M10, M13, right? So that fraction of I bias goes into this, right? And accordingly, I can change the GM value so that I can change the resistance of that branch, right? And what is the feasibility we got over here is that I can reduce the value of Miller capacitance because I have introduced the somehow zero, which is also called as the indirect compensation, right? So that we can get something like this response. Phase response is not so bad because we are getting what principally we are doing is that here what what uh, what we are having is that P1 and P2 is very close, and after that zero is coming after UGB, and phase margin is degrading. What we have done is that we have made it, because I know that the moment I'll make the Miller, P1 will go to the lower frequency, right? P1 will move to the uh, lower frequency and P2 will move to the higher frequency at the cost of minus 3 dB reduction. But we don't want that. What we made is P1 and P2 we kept as it is, right? So that circuit is like this. We did not move anything. Circuit is like this, right? But we have added the extra path, which is like a pumping the current into this resistor, output node, right? So that we can say that here it is happening. Means we allowed to get the P1 and P2 so that we can see in a phase response, we are getting the P1 and P2, but and system is going to get unstable. But before going over there, we just moved our phase up by pumping the extra current or adjusting the phase by selecting the value of GM and CV or compensation capacitor. It is also called as a introducing the LHP 0 are there. So that two poles and LHP 0, so that second pole and 0 is getting compensated by each other, so that it's look like a single pole system. Uh, so that we can say that uh, we can improve the performance. Here I am concluding my presentation. Scaling in the technology created the opportunity to revisit the classical analog design in terms of a operational amplifier. Means now it is one of the good opportunity, because scaling has created a lot of problems in amplifier in terms of a gain, in terms of frequency. I think it is win-win. But in terms of a gain, which sacrifices this accuracy, apart from that, as the size has reduced, there is a problem with the mismatch, and other techniques like a bulb biasing and all created noise related issues. So that these kind of problems are quite evident nowadays. And particularly speaking now, there are two fields which are quite prominent. One is that automotive sensor based application, and second is very very high frequency, where PIC is coming into the picture. That PIC is nothing but a photonic IC, where people are working on a 6G and 7G kind of making the say a 6G and 7G kind of circuit, where it works on hundreds of gigahertz. Your circuit will be, so that these are some circuits people are working on, where operational amplifier is one of the prime block, whether you operate at a lower frequency or whether you are operating at a higher frequency, uh, because because this block will govern most of the specifications of a system. So that or vice versa also true. Specifications of the system also will will govern the design of operational amplifier, right? This is, I think, much more apt way to say. So that the point here is that operational amplifier, even though people think that it is a beaten dog, but it's not like that way. It is still having, there are a lot of scopes to a lot of scope to figure it out what to do next. So that just I wanted to say this thing before closing my presentation. Thank you. I think I'm too early, but yeah, you can uh, discuss the things if you. No, I think it's I'm time, right? Seven
Yeah,
minutes
I
late,
think
I
we are
guess.
7 minutes over time, but I think that's okay.
Oh, sorry.
No problem. I think. Yeah. Are there any questions from participants?
Hello,
Okay.
sir.
Yeah, please go
Hello.
ahead. Yeah.
Sir, you said that VDD to VSS 1 volt. So 1 volt means is it +1 -1 or 1 and 0?
Yeah, it is 0 volt to 1 volt.
0 to 1 volt. Okay.
Yeah,
So
means you can map it into
huh.
another way also, minus point 0.5 to plus point 0.5,
Yes, yes. Okay.
because it takes only absolute voltage into the
Okay.
consideration.
Okay.
Yeah.
Sir, one more question. So whatever topologies you showed now, so where can we refer these means topologies? Where we can get these papers?
Papers for multi-stage, generally I referred Long's paper. I think it is 2001 paper. And once you get this paper, you will find the other papers as well in their reference. In's paper is quite famous. I think it is 1996. I don't know exact title of
I think it's
this
there
one.
in the references, no, in the slides.
I did not put, yeah, means wherever it is needed or meant,
Ah,
I have mentioned it.
yes, yes. I
Uh,
think with that way you should be able to find it. I mean,
okay.
Yes, sir. Okay.
Anything else?
Hello, sir.
Yeah, Dipesh.
So, sir, is there any textbooks where from the specifications there are calculations, design calculations are given? For example, if you want to design folded cascode amplifier from the specifications, so that uh,
Uh,
design
there
point
are
of
a
view.
lot of books which I have preferred. Baker book, Jack Becker, first edition, not a first edition. That is first book what he has written. Apart from that, Razavi, Holberg, Ken Martin. I think this book are is very good to understand these concepts.
Okay, sir.
Yeah, if I may add, we have a lab session coming up next. In that, we will look at the simple two-stage amplifier to go from how to go from specifications to geometries and simulate.
I think that will be much more informative as
That is
compared
just
to.
as I mean, not all the architectures that Vinayak has discussed. It will be the basic two-stage one. But once you understand the basic one, I think getting onto the other ones will should not be that difficult.
Yeah. You can contact me offline as well on my email ID, right? So that it is not necessary that you should ask me question now also. And anyway, we are meeting tomorrow as well, day after tomorrow as well. So that is not an issue.
I think tomorrow and day after tomorrow. There is one session tomorrow and one day after tomorrow.
Yeah, exactly. Okay, I think that's all from my side for today.
Email ID. Somebody is asking email ID. I have written an email to all the participants, keeping all the uh, I mean experts in CC. So you can just look at the email you have received. Everybody's contact details are there in that.
Okay.